surprised. Just you and Michelle is here. And because you guys are just few, I can see you're even dancing. Don't worry. Let me ask you one question. You can write Michael Jackson dance there. It's okay. Now,
I'm just turning.
And be turning, that's part of dancing. We'll be talking about field, and let's see. Oh, Jesus. Really? Was I sharing my screen? I shouldn't have done this now. Okay. Now, we'll be talking about field, and what we need to learn about field is you need to write something down. Is write this. Number one, field is a region under the influence of physical agencies. Field is a region under the influence of some physical agencies. Now, such as gravitation, magnetism, and electricity. Fields is a region under the influences of some physical agencies. Under the influences of some physical agencies, such as gravitation, magnetism, and electricity. That is very instructive, very important for us to know that is a region. Now, we have two types of fields, Number one, we have two types of field. I said field is a region under the influence of physical agencies. That means any area. Now, imagine I come onto you and I do something like this. I try to do winchy around you. And then as I'm doing like that, you two are moving like this. Hey. Because you stay around me, I'm doing that thing. That thing means she's scared. Because I'm doing something like that and you are moving, that shows that that region could be a spiritual field. That's a spiritual field. But now we are talking about magnetism, gravitation, and electric field. All right, now we have two types of field. Number one, we have the vector field and we have the scalar field. We have two types of fields. We have the vector field and we have the scalar field. We have the vector field and we have the scalar field. Okay, now number one, the vector field. The vector field is the field which is usually represented by lines of forces. The vector field is one which is usually represented by lines of forces. Please, Michelle and Idani, I need you guys to use your video now. Please use your video now. Now, the vector field is one which is usually represented by lines of forces, while a scalar field is one that is not represented, by lines of forces. Now, for a vector field, example of a vector field, we have gravitational field, we have the magnetic field, and we have the electric field. I call them MEG, or we can call them GEM. That's gravitational field, electrical field, and magnetic field. Now, the other type, example of scalar fields could be temperature, density, and pressure. Michelle, please use your video now. Michelle, use your video now. All right. Michelle, if you don't use your video, I will assume you're not here, so I might have to put you back in the waiting room. If you don't use your video, I will assume you're not here and send you back to the waiting room. Okay, welcome. Now, gravitational field. Let's talk about gravitational field. All right. Very, very instructive, gravitational field. Now, we can even spend the whole day talking about this guy. This guy is so massive. because every one of us experience the effect of gravity, right? Gravitational field is a region of space surrounding a body that has the property of mass. Please write that down. Gravitational field is a region of space. Gravitational field, write that down, is a region of space surrounding a body. Surrounding a body that has the property of mass. That has the property of mass. You, because of your mass, gravitational field will always surround us. Now, gravitational force is responsible for the fact that whatever thing you throw up must surely come down. Why? Because that thing has a property of mass. Now, please write this down. Note, the force of gravity pulls every object towards the center of the earth. The force of gravity, please write that down. The force of gravity pulls every object towards the center of the earth. Now, the force of gravity pulls every object towards the center of the earth. Now, what is this trying to tell us? This is trying to tell us that gravitational force causes a body which is not in contact with the earth to fall to the ground. This means that gravitational field force causes a body which is not in contact to fall to the ground. And this means that the earth would always exert an attractive force on any object near the earth, or any object in the earth, the force would always attract it. Now, it might look as if you are not falling down. Trust me, you are always being drawn. The force of gravity is always dragging you to the earth, to the center of the earth. But you say, sir, but I'm not falling, like I'm not turning. Why you're not turning is because your mass to an extent is greater than the gravity, the force of gravity. Because the force of gravity on Earth, the acceleration due to gravity is 9.8 or approximately 10 meters per second squared. So similar, two objects of different masses can exert equal and opposite forces of reaction on each other. Let's just watch, let's just see something that has to explain gravitational field. Where is, okay, I guess I have something here for you. Okay. Now let's look at this. Right? I guess everybody's seen this.
A gravitational field is a region around one mass which affects other nearby masses. It is very weak, however, which is why the effect is only significant on large objects like the Earth. We can represent the Earth's gravitational field by drawing field lines showing the direction of the gravitational force on masses in the field. In this case, the field is radial and equally spread around the Earth. On the surface of the Earth, the gravitational field is approximately uniform because the field lines are virtually pointing in the same direction and are equally spaced. This is why we assume the acceleration due to gravity is a constant of 9.81 meters per second squared, because the change at small vertical heights is negligible. Newton's law of gravitation states that all masses attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between the centers of mass. This gives us the equation F equals minus gmn over r squared, where g is the universal gravitational constant of 6.67 times 10 to the minus 11. M is the mass of the larger body.
Now, this formula you're seeing here is something called Newton's universal law of gravitation. We are going to come to that later on. So that's just an explanation.
M is the mass of the smaller body, and r is the distance between the centers of mass of the two bodies. The minus sign simply refers to the fact that the force is attractive. For example, two bodies, one of mass 6 kilograms and the other of mass 20 kilograms, are placed 50 centimeters apart.
Okay, when we come to that formula, When we come to that formula, I'm going to play this video then so we can understand it better on. So when we come to that formula, that's not an issue. I guess we just have we are just some few notes away from that question. All right. Let me see. Okay, I think nothing is stopping us from talking about gravitational field. Okay, let's look at Newton's law of universal gravitation. Newton's law of universal gravitation. Yeah, who can state that? Who can help us out? What is state the Newton's law of universal gravitation? Somebody is browsing this out. So nobody can talk. Seriously? No idea?
Anything that goes up must come down.
Jesus Christ, are you seriously? Ella has decided to run away. She wants to go and check. Ella, I have caught you. God has dealt with you today. Ella, God has dealt with you. Michelle. Michelle, you mean you can't answer that question? When to put lipstick in your mouth so that we will know that you are here and yet you're not answering our question.
Mind down.
With this, your glasses that looks like a four-corner eyes. Francis, what about you?
Every particle attracts every other particle in the universe.
When you are,
force that is directly
you're reading it from somewhere. When I start hearing names, every other particle, you know that this guy is reading from somewhere. I've got you. Seriously? This is funny. Ella has decided to run away. It's okay. Ella, you better come back now before I send you back to the waiting room. This one is just there with her lipstick in her mouth. May God have mercy on you. It's all right. You now, Michelle, what else am I talking to? All right, let's look at Newton's law of universal gravitation. I'm going to play a video for you guys to see that. Newton's law of universal gravitation. Very, very instructive. Ella, sure you ran away. Newton's law of gravitation made you to run away with this your Miriam.
No, my mom is calling me.
Okay, mommy is all. Next time she's calling you, please let me know. Just tell me. Don't just go like that. Do you hear me?
Okay.
It's all right. Let's look at this. Okay, Newton's law of universal gravitation. You're going to watch it from here.
Newton's law of universal gravitation. He knows a lot about the science stuff, Professor Dave explains. We learned about Newton's laws of motion, but there's one more law of his to discuss, and it's a big one. It's Newton's law of universal gravitation. In possibly one of the greatest strokes of genius in the history of mankind, Newton looked at the motion of the planets in their nearly circular orbits around the sun and understood that the centripetal force causing this motion was precisely the same force that causes objects to fall down towards Earth, which we call the gravitational force. In this way, he proposed that the planets are in a kind of free fall towards the sun, just the same way that the apple that mythically hit him on the head to produce this insight was in free fall towards the Earth. The objects differ greatly in size, but the concept is the same. Newton corroborated this notion with a thought experiment. When a cannon fires a cannonball, the ball eventually hits the ground. If another cannonball is fired with greater force, it will go a little further before hitting the ground. If a cannonball could be fired with an incredibly immense force, it could produce a speed so great that the ball would never hit the ground, since it would fall at the same rate that Earth's curvature is produced. It would thus always be falling towards the Earth, but never hitting it. Such an object would be said to be in orbit around the Earth. Of course, no cannon can do this, but we have finally achieved this feat with all of our satellites and space stations, which are brought up to orbit on rockets. These are very far from Earth's surface, and they are moving with such great speed that they, along with anyone on board, are always falling towards the Earth, but never hitting it,
Now, have you not noticed? I want to ask you guys this question. Why is it that they launch satellites? Hey, Ella, stop this your head now. Stop distracting me with your head, please. Now, why is it that they launch satellites in space? And the satellites, what makes the satellite to keep revolving around the Earth, but they don't hit the Earth? Who can explain that? Have you thought about it?
Yes.
Tell me, explain. What makes satellites? See the way Idan is shaking his eyes. He knows I was not asking. What makes satellites that they don't hit the Earth? They don't hit the Earth. They keep revolving. What suspends them there like that?
Gravity.
Gravity? Nobody's saying anything.
Newton's law.
Newton's law. You better watch this thing very well so you can explain it. That's because I saw some of you, most of you are not watching this very well. Watch this very well to explain it.
That is speed.
Fires a cannonball. The ball eventually hits the ground. If another cannonball is fired with greater force, it will go a little further before hitting the ground.
Force.
The ball could be fired with an incredibly immense force. It could produce a speed so great that the ball would never hit the ground, since it would fall at the same rate that Earth's curvature is produced. It would thus always be falling towards the Earth, but never hitting it. Such an object would be said to be in orbit around the Earth. Of course, no cannon can do this, but we have finally achieved this feat with all of our satellites and space stations, which are brought up to orbit on rockets. These are very far from Earth's surface, and they are moving with such great speed that they, along with anyone on board, are always falling towards the Earth, but never hitting it, in a free fall, just like Newton's apple. This means they orbit around the Earth indefinitely at a fixed speed and radius. The same can be said for all the planets around the Sun. This gravitational force can describe the motion of every object in space, and it is the case that every object that contains mass will exert gravity on every other massive object. Of course, to feel the effects of gravity, we must be near an enormous object, like a planet. But it is completely accurate to say that gravitational force is exerted by your car, your refrigerator, even you yourself. It is just that this force is completely negligible compared to the gravitational force exerted by the Earth. Newton developed an equation to quantify the magnitude of the gravitational force between two objects, and it looks like this, where F is equal to the constant of universal gravitation, G, times the mass of the first object times the mass of the second object.
Right, everybody write this formula down.
Divided by the distance between them squared.
Write that now, everybody. Okay.
This constant, like any other constant, simply exists so that a natural phenomenon like gravity can be expressed in our own arbitrary man-made units, and it is equal to 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. These are the units that will cancel out the units on the masses and radius, so as to give a value for force in newtons. This value was not known to Newton at the time, but was determined experimentally about 100 years later by Henry Cavendish. When discussing the radius between two objects, we will take the distance between their centers rather than their surfaces, as Newton showed that the gravitational force exerted by an object depends only on its mass and not on its volume, meaning that when discussing gravity, we can treat everything as a point-like mass. He had to invent the calculus to do so, much to the dismay of math students everywhere.
When examining a system like the Earth and the Moon, we must understand that both of these objects exert gravitational force on the other, and that these forces are equal in magnitude, meaning that both of these bodies rotate around their combined center of mass. But don't forget that F equals ma, so equal forces will not produce equal accelerations if the masses are different. As it happens, the Earth is much, much more massive than the Moon, so the mutual gravitational force is able to accelerate the Moon more than the Earth, and the center of mass for the system lies within the Earth itself, which is why we simply observe the Moon going around the Earth. The same can be said for Newton's falling apple. The apple accelerates towards the Earth, and the Earth accelerates towards the apple. But the Earth is more massive than the apple by an inconceivable factor. So the acceleration of the Earth is not even measurable, whereas we can visually confirm the acceleration of the apple. Furthermore, we want to understand that an apple will fall to the Earth with the same acceleration as a bowling ball or any other massive object if we disregard wind resistance. Although counterintuitive to some, we can rationalize this if we understand that while the force of gravity is able to impart greater acceleration on a more massive object, the more massive object also has greater inertia or resistance to being accelerated. So the end result is that all objects accelerate towards Earth in the same way, at 9.8 meters per second squared. This fact is easy to derive if we do some algebraic manipulation. We know that a falling object exhibits behavior according to Newton's second law, F equals ma, where the force that generates the falling is equal to the mass of the object times its acceleration. But this force is the gravitational force, so we can also model the falling behavior with gm1 m2 over r squared, where m1 is the mass of the object and m2 is the mass of the Earth. If we set these equal to each other, the mass of the object is found on both sides and will cancel out. So we can see that the acceleration due to gravity is equal to the gravitational constant times the mass of the Earth divided by the radius squared. This means that the mass...
Okay, let's stop there. Now let's write. Now, the force, Newton's law of gravitation, I just gave you the formula, but can you state it? Can you state what, can you state the law? What does the law say? The law says that the force is directly proportional to the product of its masses and inversely proportional to the square of its radius. The force is directly proportional to the product of its masses, the product of its masses, and inversely proportional to the square of its distance of, you can call it the radius or the distance between them. So that's Newton's law, universal law of gravitation. Now let's use, I want to ask you, those mass, they are measured in what? What's the unit of mass?
Kilograms.
Okay. What about, what's the unit of radius or the distances between them? What's it measured in?
Meters.
Meters, good. Now let's solve this question. You guys should solve this question. Remember, G is constant. Did you get the value of G?
Yes, sir.
6.67.
Yes, sir.
Yeah, correct. Okay, let's solve this question. Please solve this question now. We have just less than 6 minutes to solve this question. Who's done? Oh, he's done. Wow, 2 minutes gone, nobody's done. Serious? Oh, Francis is done. Oh yeah, Francis, send your question, send your answer. Oh, yay, people are getting different answers. Oh, Jesus. 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 I need one more person to come to send me. Okay. We don't have time. Let's just play this. So you judge yourself. Hey, Francis got it. Ella into.
I know.
Francis didn't even get it totally. Ta. Is this super minus? Francis got raised to power minus 11. Ta, Francis. Ella, what did you do?
I don't know.
Ella, you don't know what you see. You see, I know what you did, Ella. You see all those things you people would do. You just put all these things like this inside calculator. You expect calculator to give you the correct answer. It's a lie. It will not work. Instead of you to have done this, multiply by this, write the answer somewhere. Then divide by the square of this. Ella will not do that. Ella will punch everything inside one calculator and expect the calculator to add the correct.
I don't have calculator.
You said
I don't have calculator. So I use hand. I use hand.
Now you now posted everything.
I'm not using my phone. My phone is there.
So you're using your
hand.
So in your mind now, you're using hand to solve this thing. Kai, Jesus. It's okay, no problem. I respect you. Shall you even tried? Michelle that didn't do anything, Ko.
She's on mute. She doesn't.
What of Idani said I just looking with his shiny eyes. Look at his eye. Look at his eyes shining. He didn't even, you see, he has disappeared from here because I called his name.
Right.
He's shining his eyes. He didn't even do anything. It's okay. But nevertheless, you guys try. At least you've known how to solve it now, right? Francis, you did not put your unit. If I can catch you. You did not put your
unit. Times 10 is to power minus 8, sha.
See lies upon lies.
I got it. I got the 10 to power minus 8.
Lies upon lies. Now listen, Michelle and Idani, you've not done your CBT. She? Oh Jesus. Michelle, you see with this your lipstick in your mouth is disturbing you. I have seen it. Idani, your eyes is disturbing you. She? You guys cannot go and do your CBT, right? You see the way he will just put earpiece in his ear and then it will block his ear as if he's not hearing me. This one will come and put lipstick in her mouth to disturb her life. I will not understand that they should go and do their CBT. I don't know what kind of thing is this one. You be using your eyes you see how many eyes you have? 4 eyes with you're not even scared of that one. You're not going to put lipstick again inside class. Why Idani now? Look at everybody. Look at Idani. Idani is wearing mask inside class again. Nose mask. My brother, is there corona in your house?
Size my shirt.
Is your shirt? It's okay. It's all right.
Yes.
Now, If Michelle and Idani, I'm going to open the CBT again for just today. Once it's 12 o'clock, that means 12 a.m., you won't see it again. If you don't do it, you have only today to do that thing. No? Why I'm going to send your assignment again for this place. Do you understand that? I'm going to send you assignment regarding this thing we just did today. All right. Have a nice time, everybody. Thank you. I hope you have no questions. I don't believe you have questions. Idani, I waited for you on Tuesday. I didn't see you. You ran away. She?
So I did not run. I was coming.
You know what I'm talking about, Sha. You and I have an agreement. We know what we are talking about. Others, you don't need to know, yeah?
So I did not run.
Idani, you ran away. We'll meet again on Monday, Idani.
So I did not run.
You did not run. All right. This one, Ella is putting her chin as if she has beers. Look at my own. When I do like this, you know I have. You don't have anything. God will not give you. Look at everybody own looks like a sheep. You know, I see there's nothing there. Now, when you look at this one, you know that there's something there. Let us pray. I beg. It's time to go. All right. Father, we thank you for today. Thank you for your wisdom. Blessed be your holy name, Lord. In Jesus' name. Amen.
Amen.
I have left you. I am signing out. Sign out. Ew.
All right.
All right. Bye.